All right, everybody, grab your notepads, pick up your highlighter. It's time for everyone's favorite subject, nucleosynthesis. No, wait, come back. I swear it's going to be fun. I'm going to do my first reaction to an advertisement. When this ad aired, I got like a million messages saying, hey, what do you think of this? Is this an accurate thing? So let's go ahead, watch Apple's new ad for their iPhone 15 Pro made from titanium. Okay, so does titanium come from the edge of the universe? No, but you probably knew that. But where does it come from? This graphic uses data from Dr. Jennifer Johnson of The Ohio State University, but we won't hold that against her for the purposes of the discussion. And it shows the origin of the various elements on the periodic table. And as you can see, there are 6 ways that the universe manufactures elements. When the universe was first born, it was extremely hot and dense. Temperatures of trillions to billions to millions of degrees as it cooled off, and really the density of a star. In fact, the entire universe was like the interior of a star. Well, what happens in the interior of a star? Hydrogen atoms smash into each other and create helium. And that's exactly what went on for the first about 20 minutes of the universe's existence. It was so hot and so dense, hydrogen atoms were smashing into each other to create helium atoms and a tiny bit of lithium. So that's where all the hydrogen in the universe comes from. Some helium has been manufactured by stars since then and other processes. Most of the lithium has. But that's where most of the hydrogen and most of the helium came from. In fact, the ratio of 25% of the universe being helium and about 75% of it being hydrogen is one of the confirmations of Big Bang Theory, because we can make these calculations of how much helium would have been produced, and it matches the exact fractions that we get. Everything other than hydrogen, helium, and lithium has come from various energetic processes. So let's go through those. One of those is what we call cosmic ray fission or cosmic ray spallation, where you have heavy molecules like cobalt or something like that, and a cosmic ray comes and strikes it and breaks it apart. Cosmic rays are extremely high energy particles moving at close to the speed of light. And they are manufactured by supernovae, by active galaxies, by the black holes at the cores of those galaxies, some even from our sun. And they are so powerful, when they hit heavy molecules, they break them apart. And that's where beryllium and boron come from. Stars will actually not manufacture those. They'll go straight from helium to carbon and oxygen in their manufacturing process and skip over beryllium and boron. Another source of these is dying low mass stars. That's the green on this table. When a star like the sun dies, it will puff out its outer layers and illuminate this large nebula, a planetary nebula. The energy being pumped out by the star at that point is so intense, it will cause nuclear fusion to create heavy elements like yttrium and tin and lead are created this way. The probability that you're going to get particles colliding with enough energy to create these heavy elements is very low, but stars are very big. There's a lot of material out there. So even the teeny tiny fraction of it has these reactions, you're going to get lots of these elements. And of course, they're more abundant on Earth because all the hydrogen was swept away or combined into water early in the solar system's history. Now, the other 3 are the most interesting. One of these merging neutron stars is something we only discovered a few years ago. A few years ago, there was a neutron star collision. 2 neutron stars, these shriveled husks of dead massive stars, collided together to create a black hole. When they did that, they created ripples in the fabric of the universe that was detected by the gravitational wave experiments we have here on Earth. And when this happened, they alerted every telescope in the world, including mine, to turn towards that to learn what we could. And the first day that this was made public, something like 70 papers were published on this. And one of the discoveries we made was that many of the very heavy elements, like bismuth and polonium, and gold was the one that caught the media's attention, are manufactured in these processes. the energy pumped out is so intense it's causing what we call the rapid neutron capture process, where you get neutrons ramming into these elements and building them up to heavier and heavier elements. You'll notice there's a few on here that are marked in gold as human synthesis. Everything else on there has stable isotopes that will either not decay or last for a very long time. When you're talking about technetium, praseodymium, and anything heavier than plutonium, those are only manufactured by human beings. They don't occur in nature at all because they would instantly decay. But the other two are the ones that are more relevant here. When you're talking about exploding stars, one is when you have massive stars that are 8 times the mass of the sun. They go off these massive explosions. When the core collapses to a neutron star black hole, the outer layers crash down and rebound, and they explode out into the universe, and that will scatter some of the heavy elements manufactured during the stellar evolution process. If you watch my Addicted to Love video, I talk in depth about how this works. And those scatters those elements into the universe, enriching the next generation of stars with heavy elements. Now that's a type 2 supernova. A type 1 is where you have a white dwarf. This is the shriveled husk of a star like the sun. And it's held up by what we call electron degeneracy pressure. That is the unwillingness of electrons to be pushed very close together. But that will only hold a star up to about 1.4 times the mass of the sun. If it goes over that electron degeneracy gives way and the thing collapses to a neutron star. That's what we call the Chandrasekhar limit. He was the first one to calculate that. When that happens, the star will blow itself apart and enrich the interstellar medium with this new material. And that's what we call a type 1 supernovae. That happens at very specific luminosities, and we use those as standard candles to measure the distance to the most distant things in the universe. Usually the way this happens is you have a white dwarf in a system with another star, and it's pulling material off of that star, accumulating mass on the surface so that it builds up until it finally goes over that limit and explodes. Most of the elements that we deal with every day are manufactured in these supernovae. So scandium, iron, nickel, gallium, chlorine, oxygen, that's where these come from. Now, you'll see that on this table, most of those elements have a mixture of the white and yellow, showing that they come from the 2 types of supernovae. But notice something else interesting. Aluminum is almost entirely from massive stars. Silicon is a mix. Phosphorus is almost entirely from massive stars. Sulfur is a mix. Chlorine, entirely from massive stars. Argon is a mix. What happens is these are what we call alpha elements. That when you have these processes going on in the star, what you have is alpha particles, helium nuclei basically, smashing into atoms and merging with them and creating heavier elements. Helium has 2 protons in it, so every time it collides with an element, it jumps it up 2 points in the periodic table. So it turns silicon into sulfur and skips over phosphorus. It turns sulfur into argon and skips over chlorine for the most part. It hits calcium and turns that into titanium. And these are what we call alpha elements. And they're really, really useful for telling us the enrichment history of stars. That if we look at the abundances of these elements and compare them to other elements, we can learn things about their formation history, what kind of stars were enriching the material out of which they formed, and so on. So titanium, it's an alpha element. It's a calcium atom that got lucky, that got hit by another alpha particle, bumped up to titanium, and that's where it came from. So the titanium does come from the cosmos, but it doesn't come from the edge of the universe at the dawn of time. It comes from the same supernovae that created the calcium in your teeth, the same supernovae that created the oxygen that you're breathing, the same supernovae that made the silicon that makes the phone, that makes my computer work. So I'll give this maybe 2, maybe 3 face palms, because yes, it's true that titanium comes from us from explosions and violent events, but it doesn't come to us from the edge of the universe. It comes from us from right home, right out of the stuff we were made of. Because as Carl Sagan said, we are star stuff. Every element in your body, other than hydrogen, was manufactured in one of these violent processes from stars. And the hydrogen in your body that makes up the water in your body, and we're mostly water, was manufactured in the Big Bang. So you're a mix of the material that formed when the universe was first created and the material that has been forged by stars ever since. And so is your iPhone. It's not anything special. Sorry, I'm an iPhone person. I'm recording this on an iPhone, but it's not from the edge of the cosmos. So that was a little fun. I have a couple more videos in the can ready to roll out over the next few weeks. Until then, I'm Mike Siegel. I write for Ordinary Times. Thank you for watching.